In class, we've been talking a lot about heat. Today, we're going to talk about heat and the different variables that impact it, and specifically the change in heat. And so first, heat is the total energy, which means EK plus EPH. The variable that we use for heat is a lowercase q. And since we're going to be talking about the change in heat, then it's going to be delta Q. The little triangle means change. The unit for heat is going to be joule. Energy is measured in joules, and so it's going to be a capital J for the joule. As far as a graph, we're not going to have a graph because our graphs are going to compare our variable with the change in heat. And so we have three variables to consider. The first one is mass. Our definition for mass is the amount of particles in a system. Our variable for mass is a lowercase m, and our units for mass are grams, a lowercase g. And so we've talked about how having more mass means you have a higher amount of particles, which means more collisions, higher number of collisions, which means a higher change in heat. So if we do a graph of mass versus change in heat, it's going to be a positive relationship. The more mass, the more particles, the more number of collisions, the higher the change in Q. Our second variable is temperature. And temperature is the average EK of particles, the average kinetic energy of particles. So far, we've talked about how fast they move, but all particles aren't going to be moving at the exact same speed at the exact same time. So temperature is really a measurement of the average kinetic energy of the particles in that system. We know that our variable for temperature is capital T. However, we're going to be talking about the change in temperature, not just 1 point of temperature. And so the change in temperature is calculated by taking the final temperature minus the initial temperature. So TF minus TI, final minus initial. That's very important. So put that on your things to study so that way you don't subtract the wrong one or you'll get the wrong answer. So it's final temperature minus initial temperature. Our units are degrees Celsius. And the higher temperature we have, the higher the average kinetic energy. Kinetic energy is how fast things are moving, so our velocity. Higher velocity means a higher number and force of collisions. Think about it this way. If you are a little freshman, and the little freshmen on the first day of school are always running with their head down and their big book bag, and they're darting through the halls. Well, that little freshman, because they're moving faster, is going to hit you. If they bump into you, they're going to hit you with more force, and they're going to hit more people, higher number of collisions, versus the too cool for school senior that's walking super slow and not a care in the world. They bump into you, they're going to bump into you a lot less, and they're not going to have as much force behind that bump. So that means they're going to transfer the freshman with a higher temperature, higher average kinetic energy, higher velocity, higher number and force of collisions is going to transfer a higher amount of heat. So a higher change in Q. That means that temperature compared to the change in heat is going to have a positive relationship. The higher the temperature change, the higher the change in heat. I'm going to change this graph so that it says change in temperature. Well, maybe I'm not. Dag nabbit. Well, it should be a change in temperature there. There we go. So change in temperature. Specific heat capacity. This is a new one. Specific heat capacity is talking about the amount of energy needed to change 1 gram by 1 degree Celsius. Our variable for specific heat is a lowercase c. Our units for this, since it's the energy needed to change 1 gram by 1 degree Celsius, energy is on the top, gram is on the bottom, and degrees Celsius is on the bottom. The amount of energy needed to change 1 gram by 1 degree Celsius. So basically what this is when we have two different metals. So different materials have different specific heats. All materials have different specific heats. So for example, copper is more dense than aluminum. And so copper has a higher particle mass. If I have the same number of particles, copper's particles are larger. So the particle mass is higher. A higher particle mass means a lower velocity. Think of it this way. If there's a tractor trailer side by side with a smaller vehicle, let's say a little Mini Cooper, and they're both sitting at the stoplight. When the light turns green, the Mini Cooper is going to move faster. That's because the larger tractor trailer truck has more mass. So more mass means it's going to move slower. Since it's moving slower, it's going to have a lower number of collisions, which means there's going to be less transfer of heat. So higher particle mass, less velocity, less collisions, less change in heat. So this means that our specific heat capacity, the change in heat is going to depend on that heat capacity. The more dense it is, the slower it's going to change. The less dense it is, the more it will change heat. These are the variables that impact our heat. And so hopefully this will help you to better understand our equation, the variables that go into it. And so we talked about this. We talked about how the change in Q is going to depend on the mass, the change in temperature, and our specific heat, or delta Q equals MC, I wrote that backwards, MC delta T. MC delta T. Doesn't really matter what order you write it in. This is just kind of what we remember. I call this the MCAT formula because C delta T, the delta looks kind of like an A, so it's delta Q equals MCAT, MC delta T. When we look at our units, my unit for energy is joules, equals grams times joules over grams degrees Celsius times the change in temperature, so the change in degrees Celsius. This makes sense because when we turn it into our ratios, Dorman, you're going to have me do ratios. I'm just going to show you how it works. Ratios aren't as bad as we think they are. And so when I look at my ratios, my grams cancel out, my degrees Celsius cancels out, so I end with joules, which is what my Q is. Hopefully this helps you to better understand heat, the change in heat, and specifically the equation that we use to calculate the change in heat.